Hi, thank you, thank you. And so, okay, and you can hear me all right? Nice to be here. Okay, cool. Well, it's good to be here. I did my PhD at CMU. I ended in 2015. I don't think there was nearly this big of a local group when I was here, so it's cool to see a lot of questions. What? There's this mic. Can you hear me? Not very well. Not very well.
Okay, I think you would have to speak directly.
Speak directly to this.
Sorry.
And I'll try to speak up. So I want to start actually with a demonstration. Can I get 2 volunteers to come up? Raise your hand if you want to volunteer. We got 1, 2. Okay. Let's come up. Let's do a quick demonstration actually. I don't do it here because I want to be echoing. Yeah. Okay, guys. So. Okay. Okay. Still echoing a little bit. Okay, so we got 2. What are your guys' names? Salve. Ayud. Okay, so we're gonna play a few hands. I got here just all the hearts, 13 card deck. And so this game is called One Card Poker. So we have both players in view with a stack of chips here. And so I'm gonna deal each player 1 card and from a 13 card deck. And so you're allowed to initially ante 1. So here, both of you guys, you can stand here. So you got 1 and 1. So here's the pot of 2 right here. And so I'm gonna deal each of you a card. And so what was your name again? Salve. Okay, yeah. You can go first. So I'm gonna deal 1 here and 1 here. So you can either look at your card, keep it to yourself, or you can look at your card. Okay, so you can either bet, you can either check or bet 1. So what we can do?
I'll bet.
Bet, okay, so you put your 1. Okay, so now you can either call or you call. Okay, he calls. So let's see what they have. Let's see, what card do you have? You got a 6, and the higher card wins, of course. And we got a, oh, you called with the 5, okay. Look at your card. You want to check or you want to bet?
That's not it.
Yeah.
Okay.
Yeah.
So
The desktop isn't showing it has audio.
okay. Well, let's see what you guys had. Just so we bluffed him. No, he didn't. No. But he had such a bad hand anyway. Okay. Good. I think we. Thank you. Thank you for this. So this game is this very simple game. It's called One Card Poker. And so as it turns out, this game and actually every game has what's called a match equilibrium. Now, for special games like this is a 2-player zero-sum game, where basically one player wins when the other player loses. And so you can call a Nash equilibrium optimal. Actually, you can actually play against optimal play at this site, Professor Jeff Gordon here on the website. But you can see here in this table, the top one is for player 1. So actually, the numbers are pretty aggressive out. So player 1 should actually bet sometimes with the 2, 3, and 4. We saw like a bluff with the 4, and then should actually sometimes, like with the ace and king, should sometimes check as a trap. And so this strategy guarantees no matter what opponent you're playing against, that you're going to win or tie. And so that's pretty compelling. So actually, player 2 has a slight advantage, about 6 cents. But if you switch roles as player 1 and player 2, no matter what opponent you play against, you're guaranteeing an expectation that you're going to win or tie. any given hand you might lose, right? The king against an ace, you're going to lose, but on average, over all possible hands, you're unbeatable. And so that's pretty compelling. And so Nash equilibrium is the central solution concept in game theory. And this shows it's pretty compelling, right? To be unbeatable in this game. And notably, actually, due to John Nash, it's known that every finite game has a Nash equilibrium. So we know that one always exists. And so briefly, the definition of Nash equilibrium is a vector of strategies for all the players, such that no player can improve their payoff by deviating to another strategy. And for those of you who followed the poker AI over the last decade or so, there where computers beat the best humans in different variants, that was the goal of the computers, was to approximate Nash equilibrium in that game. And so they did a pretty good job, and so it's pretty compelling. Now, in this talk, I'm actually going to argue that Nash equilibrium on its own is not sufficient. If we want to make important decisions in high-stakes skill scenarios, and when I say high-stakes, I don't just mean like poker with the high buy-in. I mean, if you have self-driving cars, they have to reason about how the other cars are going to act. National security, would we fire a missile, they might be this. And so you're reasoning with multiple agents and there might be lives at stake. And so I'm going to argue, if we want to translate game theory and these models and algorithms to these important scenarios, that Nash equilibrium is not sufficient. I'm going to talk about three distinct shortcomings of Nash equilibrium and talk about some of my recent research that addresses it. So to start, let's look at this example game here. And so we have two players. We have the row player is going to choose C or D, and the column player is going to choose A or B. And so Nash equilibrium is going to tell us that the row player should choose D, and the column player should choose A. And to see this, we can see if the row player switches to C, he's going to go down from 9.01 to 9, and so do worse. If the column player switches to B, they're going to go from 2 to 1.99 and also do worse. And it turns out the only Nash equilibrium in this game is D and A. Now, maybe you can see a problem with this, is that if we're not right, if the other player, the column player actually does do D, we're going to get this negative a million. And you could make this even more extreme. It could be negative a billion or a trillion, it could be lives being lost. If we're a little bit wrong, if B actually chooses, instead of 2, they get 1.99, they choose this. We do much worse as player 1. And so Nash equilibrium is not really ideal in this situation, right? If we play C instead, we lock up 9, and we have no risk of this really bad payoff. And so the issue here is that Nash equilibrium assumes that all players are perfectly rational. It actually assumes a little more. It assumes that the opponents think that we're rational and common knowledge of rationality. But really, do you really want to risk, many lives being lost because you're just assuming that everyone's 100% rational? Probably not. And so this is a limitation in Nash equilibrium. Now, on the other hand, there's something called a maxi-min strategy that basically is a really safe, it really is very conservative, safe strategy that says, okay, I want to play in a way that has the best worst case performance. And so, yes, this would guard against that really terrible behavior, but it would also cause us to be really conservative, right? If you have a self-driving car wants to minimize its worst case performance, it probably would never go anywhere, because if you go anywhere, you might have a crash. And so neither of these are ideal. Nash equilibrium is risky, like we just saw, and maxi-min is going to be way. So I came up with a new solution concept called safe equilibrium. And so basically at a high level, first for two-player, this is for any number of players, but first for two-player. So each player, basically, we're going to view them as irrational with some probability epsilon I for player I. And rational probably 1 minus epsilon I. And epsilon's a small number. So mostly they're rational, but there's some small chance that they're irrational. And so we don't know exactly in what way they're irrational. And so we're going to assume that they're irrational in the way that's worst for us. Now, if you have more information about it, maybe you can have a better model. And so basically, we're assuming both players are playing the best response with probably 1 minus epsilon I. and that they're playing the worst case thing for the other player would probably be epsilon. And so in the extreme, if the epsilons are 0, this is just Nash equilibrium. Now, since we ourselves, we can say we're player 1, and so as a special case, we can set our own epsilon to 0 because we're but in general, we could have all the epsilons be positive. And so we can generalize this to n players by assuming we're player 1, we're sort of a special player. And so we're playing the best response. All the other players, probability epsilon I, they're doing the worst case thing for us, probably 1 minus epsilon I, their best response. So everyone is pretty much rational, but there's some epsilon that they're doing something crazy. And so we want to, be robust to that. And so this is just a little more formal what I just said. I'm not going to go through it again. And so one of the results, so for Nash equilibrium, the key results are, that it always exists. And so I show that for any values of these epsilon parameters that epsilon safe equilibrium does always exist. So that's good. I also show that the computation of it is p-pad hard, which essentially means it's kind of like NP hard for those of you who study complexity. It's viewed not that there's no polynomial prime algorithm, which this is the same as Nash equilibrium. Now, if you play a zero-sum game, it's either there's polynomial prime, but in general, it's p-pad hard. So this new safe equilibrium concept has the same existence and computational properties as Nash equilibrium. Now, I mentioned for n-player games, we have, we're the special player, and the other players have their epsilon. Went through this already, and so we actually have the same result for n players, that it always exists, and that is p-pad hard. And so let me go through 2 quick examples here. So the game of chicken, you might have seen if you've taken a game theory course. So we have 2 players, and they can either go straight or they can swerve. And so if they both go straight, they're going to have a collision, and they both get -10, which is not great. If one swerves and the other goes straight, the one who swerves loses a little bit, and the one who goes straight gains a little bit. So, so this game actually has 3 Nash equilibria where 2 of them where one goes straight and the other swerves, and then there's a mixed one where they both swerve with probability 0.9. Now, if we set our own epsilon 1 to be 0, so we are rational, and we vary the other players epsilon 2, we don't know exactly how irrational they are. Now, if it's, it turns out that if epsilon 2 is between 0 and 0.1, that the Nash equilibrium, the 0.9 is epsilon safe. And if epsilon 2 is between 0.1 and 1, that this maximum strategy, the maximum is to always swerve, which is obviously, the safe thing to do. That's epsilon safe equilibrium if epsilon 2 is between 0.1 and 1. And so now the safe equilibrium doesn't have to be just the Nash or the maximum. For example, if we set epsilon 1 to be 0.05, and epsilon 2 to be 0.15, it turns out that the epsilon safe equilibrium is to swerve with probably 0.95 for player 1, and for player 2 to not swerve at all. And so that's different from the maximum and the Nash. And so, this example demonstrates this new solution concept. So let me give one more example. This is a security game. And so here we have the row player is choosing, there's 3 targets, and they're choosing which one to defend, and the column player choosing which one to attack. And so naturally, if we're defending the one that they're attacking, as the row player, we're going to get a positive payoff, and otherwise it can be negative. And so here, the Nash equilibrium is these probabilities of defending 0.31, 0.46, 0.22. The maximum, the safe strategy, is this other probabilities 0.61, 0.01, and 0.03. Now, if we set our own epsilon to 0, we're rational, and we vary the epsilon with the other player. It turns out that between 0 and 0.31, that the Nash is epsilon safe. Between 0.569 and 1, the maximum is safe, and for this interior region, 0.31 and 0.56, that this other strategy is epsilon safe. And so basically, this shows that that safe equilibrium might differ from Nash and maximum. So it's a different solution concept. And so let me move on now. So actually, you may have heard of some of these equilibrium refinements. So safe equilibrium is distinct from Nash equilibrium. Now there's a lot of solution concepts that are subsets of it. The reason for this is that in a lot of important games, there are more than one Nash equilibrium. As we'll see, there can be infinitely many. Even in the one-card poker, there's infinitely many. And so if we want to create a real agent, we want to pick one strategy, right? Should we pick an arbitrary Nash equilibrium, or maybe one is preferable to another? And so I'm going to talk about a new solution concept I've come up with specifically for sequential imperfect information games, such as poker, that's going to single out a Nash equilibrium that's more preferable. And so the first part of this is going to be a little bit sort of abstract, but I'm going to talk about a poker example that hopefully will make it more concrete. So I'm not going to talk about all of these. There's a lot of different refinements that have been proposed. I'm going to talk a little bit about trembling imperfect equilibrium, which is one of the most prominent ones, which this is what I came up with, and it's good background for where I'm at. So trembling imperfect equilibrium. So we have our original game G, and so we're going to define a perturbed game, which is the same as G, but require the players to play any strategy with positive probability. And so we say a strategy profile in G, call it sigma star, is a trembling imperfect equilibrium. If there's a sequence of these perturbed games that converges to the original game, in which there's a sequence of Nash equilibria, these perturbed games that converges to sigma star. And so you can think of these perturbed games like G sub epsilon, where say epsilon 0.01, everyone has to choose every action at least 0.01, and then you get a 0.001, and then 0.0001. And so if that is converging to G and equilibria converges to sigma star, then it is trembling imperfect. So it's been proven that every game has a trembling imperfect equilibrium. And for games like poker, it's analogous. We're basically require them to play positive probability on every action. So, so here's a game that demonstrates how this is interesting. And so in this game, there's two pure equilibria. We have UL is an equilibrium and DR is an equilibrium. So now let's look at UL. Assume that the role player is going to tremble and play a little probability epsilon on the D. And so if you look at player 2, if they play L, they're going to get 1 plus epsilon. They're going to get 1 minus epsilon times 1 plus epsilon times 2. So they're going to have 1 plus epsilon. If they switch to R, they're going to get 2 epsilon. So for epsilon being a really small number close to 0, the L is going to do best. 1 plus epsilon is going to be a lot better than 2 epsilon. So player 2 is still going to want to stick with L. And the same is going to hold, since this game is symmetric, the same is going to hold for player 1. And so even if we allow players to tremble a little bit with epsilon, the UL is still going to be robust to these trembles. And so now it turns out, I'm not going to go through the analysis, but for DR, this does not hold. If they tremble a little bit epsilon, the players are going to want to switch what they're doing. And so UL is trembling imperfect, DR is not. And so you can think of this as saying, look, UL is robust with some small amount of irrationality of the opponents. So that's kind of compelling for why that's better than equilibrium. So and so like I said, this part's going to be a little bit abstract, but I'm going to connect it to an interesting poker game very soon. So so I'm going to be considering a class of games where we have 2 players. Player 1 is dealt. We can think of this as a card, like a poker hand, dealt by the information tell 1. So player 1's dealt a hand. Player 1 then chooses some action, which you can think of as like a bet size. And then player 2 observes the action, but not the card of player 1. And then player 2 chooses an action, which you can think of like call or fold. And then they get a pay. And so we can also generalize this to longer games like full poker where you have multiple actions, but I want to start with a simple scenario here. And so now suppose we're playing this game and we're following a Nash equilibrium, sigma star, and player 1 takes an action that they should never take. They bet some weird size, they bet two times the pot, and that should never be taken under the Nash equilibrium. And so we've observed something that's inconsistent with the equilibrium that we're playing a part of. And so since we're playing an equilibrium, we're guaranteeing that they can't get benefited by betting the suboptimal side. However, we might not be playing optimally against that size. All we're doing is ensuring that they don't have a benefit to deviate from the equilibrium sigma star to this suboptimal A1, but we might have a whole range of things that do this. So in this case, trembling hands perfect equilibrium might be useful because it's assuming not that they're doing probability 0 on that action, it's assuming there's some epsilon, and so it's building that into the solution, and so it's going to guarantee that we're doing something more intelligent in response to that suboptimal bet, even though he should never be making. And so it's because it has these trembles, and so this is useful. However, so I'm going to be presenting a new solution that I think improves on trembling hand perfect. And so let me just step back for a second. We know that game theory assumes that everyone is perfectly rational, but in this setting, we've observed something that's clearly irrational. And so what does game theory say? And so I think that the core assumption, I think, should be, well, let's assume that the players are as rational as possible, given what we've observed. We've observed something, they've done something irrational, but let's still assume that they're rational other than that. And so trembling hand perfect equilibrium is a bit extreme because we're now assuming that they're trembling everywhere. Every action, they might, other bet sizes, other hands, they're doing some epsilon tremble. All we know is that they're betting A1, that this is taking this action that's suboptimal with some hand, some private information, but they might not be trembling everywhere. And so, so I'm going to consider a solution that only considers trembles that are consistent with what we've observed, not necessarily trembles in every situation. And this motivates this new solution concept called observable perfect equilibrium, which the definition is sort of analogous to what we just saw. We're going to have a sequence of these sigma stars observable equilibrium, but there's a sequence of these perturbed games, but the perturbations are a little different, in which player 1 is defined to play A1 that comes to a probability, which converges to G, which is a sequence of equilibria that converges to sigma star. So it's like the definition of trembling hand perfect, but the perturbations only have to agree with what we've observed. They don't have to be at every possible situation. And so, I'm going to skip over this. So I can prove that this is, a Nash equilibrium. It's a refinement of Nash equilibrium. I can prove that it always exists and can be computed efficiently to play zero-sum games. But let's get to the poker example here. So, you know, poker AI has a lot of different challenges, right? I mean, for no one that Texas Hold'em, right? So it's a huge game, and so there were abstraction algorithms that make the game smaller that have no performance guarantee. There's real-time endgame solving, again, has no performance guarantee. There's equilibrium algorithms like counterfactual regret minimization. They don't guarantee convergence or any performance guarantee for more than 2 players. Now, it turns out, even ignoring all of these challenges, even looking at a simple game that we can solve that doesn't have these challenges, we have an additional issue, is that there can be many equilibria. Actually, there can be infinitely many Nash equilibria, and some might be preferable to others. So even if we find one, that might not be what we want. So we don't even know what the right solution concept is, and hopefully this new concept I come up with is going to improve on that. So so let's look at this. Is probably the simplest possible no limit poker game. It's in mathematics poker by 10. This is called the clairvoyance game. And so player 1 is dealt a winning hand with probably 1/2, and a losing hand with probably 1/2. So you can think of like a 3-card deck, and player 1 has an ace 50% and a queen 50%, and player 2 always has a king, like a medium, a bluff catching game. And so both players initially ante, or they have chip stacks of N, and they ante 50 cents. So there's $1 in the pot. And player 1's allowed to bet any amount. So let's assume they're integer amounts. And so player 1 can bet 0, 1, 3, 3, 4, etc. And the player 2 can call or fold. So it turns out that, so this game can be solved analytically, it's mathematics and poker. If you're interested in these types of simplified games, I recommend the book. So it turns out player one should bet N, which is all in, with probably one with the winning hand. So even if he has $1 million in his stack and there's just one chip in the pot, the optimal size is to go all in for $1 million with the winning hand. With the losing hand, you sometimes have to bluff, and so it would probably be N over 1 plus N. You bet all in with the losing hand, otherwise you just give up and check. Now, player two, this is the solution that was computed in mathematics and poker. Player two, facing a bet size of X, is going to call with probability 1 over 1 plus X. So facing the all in, they're going to call 1 over 1 plus N. And so this game is pretty simple, but it's actually ideas based on this have been used in some of the strong Texas Hold'em agents for interpreting bet sizes for the opponent that are outside of our abstraction. So anyway, this isn't quite the end of the story. So here, this is the solution they came up with. Now, it turns out that if we face, so we know player one should bet N, should go all in. It turns out if we face a suboptimal size X, we don't have to call exactly with this 1 over 1 plus X. We only have to call with such a probability that dissuades player one from wanting to switch either with the strong hand or the weak hand to betting this X. So you can think of X as like a pot size bet, and N, say at least 3 is like 3 times the pot. And so they should never bet pot. But we only have to dissuade them from wanting to switch to that with their good hand or their weak hand. So it turns out we only have to call somewhere in this interval 1 over 1 plus X to N over X times 1 plus N. And so this is actually an infinite interval. And so there's infinitely many strategies that player two can use in response to the suboptimal bet size. And so this is actually, like I expected, if humans actually play this game, you're not probably going to see if they have a stack of $1 million, they're not going to go all in for $1 million. They might bet pot or half a pot or something. So it's pretty reasonable that a human would bet a suboptimal size in this game. And so we want to have the best possible strategy in response to that. And so you could make an argument for calling at this lower end of the threshold, where basically you could say, well, if they're betting X, they don't even know that they should be going all in. And so maybe think of like we're in the game where they think they can either check or bet X, and so we should call 1 over 1 plus X. This sort of assumes that you know about how humans play and how humans are thinking about the game, because you could also make an argument for calling at the upper threshold where, look, the human knows he should bet all in, but he doesn't know he should be checking with the weak hands. And so we want to prevent him from there. And so without any additional information about how the human opponent or the opponent is reasoning, we'd like to have a theoretically principled approach. And so how are we going to do that? So let's just assume N equals 2 for now. So they have 2 in their 2 chips, 1 in the middle. And so player 1 can either bet 0, 1, or 2. And so the optimal strategy, player 1 should bet 2 with the winning hand always. Bet 2 2/3 of the time with the losing hand. And should check, give up 1/3 of the time with the losing hand. Player 2 should call the bet of 2 with probably 1/3, facing the suboptimal size of 1. Player 2 should call somewhere in the interval 1/2 and 2/3 of the time. So somewhere between 1/2 and 2/3. And so I've talked a little bit about the extensive home games and game trees. This is an example of what that looks like, a little bit different from matrix games. So the question is, what should player 2 do, right? They could call it probably 1/2, 2/3, somewhere in the middle. And so now the trembling hand perfect equilibrium that I mentioned earlier says that player 2 should call the probability 2/3, which is at the upper end of the threshold, which actually goes against what the sort of intuition I described earlier was. And it turns out these other solution concepts, quasi-perfect equilibrium and one-sided quasi-perfect equilibrium, also say that you should call probability 2/3, which my intuition is not that that's the right solution. Now, the new solution that I propose, observable perfect equilibrium, and I have full derivations of this in the paper. I'm not going to go through proofs, but this says you should call it probably 5 balance, which is in the interior of that region, it's not simply the average of it's not the average of 1/2 and 2/3, but it's somewhere in the interior of that region. And so some intuition behind that solution is that player one, we don't know the exact way. And player one's betting the suboptimal size. We don't know exactly how. Are they doing this with the strong hand, with the weak hand? We don't know why they're betting 1 instead of 2. And so player one is actually, if we're calling probably 5 nines, player one is losing an equal amount in its expectation by betting 1 as opposed to 2 with their strong hands, or as opposed to 2 or 0 with their bluffs. While the other equilibrium, the other call percentages make player one lose an unequal amount, lose more with 1 type of mistake. And so this is kind of compelling. This is saying, well, if we really don't know the kind of mistake the opponent is making, we need to have a uniform prior over that. This is the best thing to do. And so I think this is pretty compelling. I think this is the right solution concept for sequential imperfect information games. So now I'm going to move on to sort of the final portion here. And so opponent modeling. So Nash equilibrium, one thing you could do if you're playing repeatedly against an opponent over and over again, you could just play Nash equilibrium. Like in the 1-card poker, you could just follow that table. You know, yeah, you would randomize separately each time, but you could just play that over and over and over again. Now, that's not going to do any adapting. What if you have observed your opponent that they folded every single hand? You might want to adapt and take advantage of that. And so just playing a Nash equilibrium is not going to do that. Even if there might be historical data or observations available, it's not going to take that into account. And so I'm going to show that if we do opponent modeling, we can do significantly better against a range of realistic opponents than just playing a Nash equilibrium. And I'm going to be showing experiments in 3-player poker, which I'll describe. And so a few features of the approach that I'm going to be describing. It's computationally efficient and it is scalable to large games, even though I'm just going to present results in a smaller game. It applies to any number of opponents. It's not just for 2-player. It doesn't assume that there's any historical data available. Now, if there is historical data, you might, the opponent you're playing against, you might have a lot of data on them. You can incorporate that and improve performance, but there might not be any data, and our approach is still going to work. We're going to assume the general setting of partial observability of their private information. So in poker, as you know, in some hands, if it goes to a showdown, you see what card they have. If you bet and they fold, you don't see what they have. So this is sort of the hardest, more general setting. In special cases, there's full observability and no observability. Our approach is also domain independent. It's not specific to poker. It only assumes that we've access to these partial observations. And so, so here, this is some prior work for 2-player, but it gives sort of a very high-level approach of what we're trying to do for opponent modeling. We're sort of in the Bayesian setting, some Bayes rule of probability. And so, at a high level, this is for 2-player. We assume we have a prior. Now, I'm going to talk a little bit more about where that is going to come from, because I mentioned, look, we might not have historical data. So we have some prior distribution on what the opponent is doing, and we have some response functions, which we can just view as a best response. And so initially, we're going to have an opponent model. This bar is just expectation. So assume that the opponent is playing the expectation, the average of the prior. And then we're going to play a best response to that. And then for each time step, we're playing against them over and over again. We collect observations of their play. We see how they played the next hand, for example, in poker. We update our computer posterior using Bayes rule. We have our prior, we have our observations, we combine them, we get a posterior, we compute the mean of this posterior, and then we play a best response to this and just repeat this over and over again. So this seems pretty straightforward. However, some of these are there's some challenges here. First off, where is this prior going to come from? Like I said, there might not be historical data. Second off, it might not be easy to how do we compute the posterior, right? This is a full distribution over infinitely many mixed strategies. It might be hard to compute, it might be hard to represent, and then it might also be hard to compute the mean of that. So this is a high-level approach to what we'd like to do. We also are going to extend this to more than 2 things. So there are some challenges here, even though they might look pretty straightforward. So, so here's the main algorithm we're going to use. It has a couple parameters I'll get to in a second. So the idea here is that we're first Well, we're going to have a default strategy, sigma star for ourselves, which is going to be an approximation of Nash equilibrium. So we don't assume any prior data, but we assume we can approximate a Nash equilibrium of the game. We're going to start off playing that as our default strategy. And we're going to assume as a prior for the opponents that the mean of the prior is this approximate Nash equilibrium default strategy. And we're going to assume they're playing a Dirichlet distribution, which is a sort of standard probability distribution with the mean at that prior, at the sigma ij. And so we're going to start off by doing simulating k different strategies for each opponent in each position. So like in 3-player poker, you switch roles and you can have, this player acts first and then this player acts second. So for each player position, we're going to create a model. We're going to simulate k strategies from this prior distribution. I'm going to go over in a second how exactly we do that. And then for each of these, we're going to initialize the probabilities of these k samples all to be equal to 1 over k. Then we have this sort of burn-in period. So with this parameter h, the first h iterations of the game, we're not going to do any exploiting. We're just going to observe. We're going to follow our default strategy, observe what the opponents do, and we're going to update the posterior. I'm going to describe how we do that. And then after this sort of burn-in period ends, for the remaining iterations, we're going to continue to update the posterior. And then we're going to play a best response. We're going to compete and exploit the opponent and take advantage of our opponent model. And so let me elaborate a little bit on some of the subroutines here. So how are we going to create these samples originally? So there's a few parameters. One of these epsilon actually is not that different from some of the epsilons we saw earlier in the talk. And so one of the issues when you're doing Bayesian analysis, you don't want to have probability zeros in the prior. Because if you have a lot of zeros and then you actually observe someone do something, that doesn't really make sense to you because you assume that couldn't happen. And so we're going to initially set things that are below epsilon, set them to epsilon so that we don't have probability zeros in our product. Like I said, the prior is just going to be approximate Nash equilibrium. Now we're going to sample from a Dirichlet distribution centered at the strategy. You can sort of think of this like, a normal, like a Gaussian distribution has, you can have mean zero and variance sigma squared. You can sort of think of this like a multi-dimensional Gaussian distribution centered at this equilibrium strategy. And so we're going to pick k samples that are all going to be sort of kind of close to it. This parameter eta is sort of like the sigma squared in the Gaussian distribution. It's going to control the variance of it. And so we're going to basically, for each opponent in each situation, we're going to take k samples from this distribution, and that's going to sort of approximate our product. Now, once we're updating the posterior, we observe a play in the game. And so we're going to look for each of these sampled strategies. How often would they have taken the plays that we saw? We observe, okay, player one bets, player two calls, player three folds, and they had a recent king. And so you want to say, how often would the given sampled strategies have taken that line, done something consistent with our observations? We're going to update the posterior by multiplying by the prior times observations, and then we're going to normalize. So this is basically just Bayes' rule. And here the prior is going to be the posterior from the previous round. And then once we've computed the opponent model based on the posterior, we're going to compute the opponent model by assuming that they're playing in proportion to these posterior probabilities. So each of these sampled strategies is going to take a given action with some probability. We're going to multiply that by the probability the posterior gives to that sampled strategy, and we're going to come up with the opponent model like this. And so, and then we're going to best respond to this. So let me talk a little bit about 3-player poker, which is what we're going to run the experiments on. So this is a simplified version. It's limit poker, and it was one of the games in the AAAI computer poker competition for several years. So there's a 4-card deck. Each player is just given 1 card. There's ace, king, jack. And so basically, it's like the game we saw, but there's no raising allowed. So as one example, we can have suppose the players were dealt a queen, king, and ace, and so player 1 checks, player 2 checks, player 3 bets with the ace, player one holds with the king, and then player two calls with the king. In this case, player three is going to win out of 5 because David is the king. And so player three is going to profit 3. Player one is going to lose 1, just the end, and player two is going to lose 2. So this is 3-player Coon poker, the game we're going to run experiments on. And so for the experiments, so actually when I was a professor, I taught an undergrad AI course, and I had the students create teams and they need to make an agent for this game. And so I have 10 agents that were made by the students for this project, and their grade was in part due to how their performance. So they had incentive to make good agents. And I'm also going to include 3 exact Nash equilibria. And so in the experiment, we're going to have 14 agents, the 10 class agents, 3 Nash equilibrium strategies, and then our new opponent modeling strategy. And so the class agents, they used a wide range of things. They could do whatever they wanted. Some used neural network, some used counterfactual randomization. And so the Nash, so there's a paper actually, it's by Peterson, Savron, and Sturtevant. And so they look at this game, and actually it's non-trivial computing Nash equilibrium in this game. They single out a robust subfamily of equilibrium. And so the 3 equilibria we're going to use are going to be sort of at the upper end bound, the lower bound, and the midpoint of this family that is. And so we have these 14 agents that we're going to use in these experiments, and we're going to use the same results, the same rules as in the poker competition. So for each group of 3, we're going to run 10 matches of 3,000 hands each. So they're playing 3,000 hands over and over again. We're going to do each of the permutations. There's 6 permutations with the same cards. So this reduces the variance, and so this duplicate. This is a common method for reducing variance, and it's used in the poker competition. So for our agent, I mentioned a few different parameters. The epsilon is sort of the rounding parameter. We're going to use 0.05. We're going to use k as the number of samples, equals 10. We're going to use h equals 10 as sort of this Vernon period. And then this variance Dirichlet parameter is going to have 4. And I'll talk a little bit about sensitivity of these at the very end. For our default strategy, sigma star, we're going to use the lower bound of the equilibrium, which have been shown to be the best. For the prior strategy means, for the opponent, we're going to use the midpoint of the equilibrium. That is that it has fewer of these zero probability actions, which I mentioned can be problematic when you're using Bayes' rule. And so this is how our agent is going to work. And so here are the results from these experiments. So our agent, this MBBR is that one, and then there's 3 Nashes and 1, 2, and 3, and then the 10 class agents. So you can see that the opponent modeling did the best. It got 48, and it did much better. The best Nash only did 37. So the Nash ones did pretty well compared to the class ones, but opponent modeling did much better than the Nash agent, all 3 of them. And they're exact Nash equilibria. And so these win rates, these numbers are the win rate per hand multiplied by 1,000. So 30 means that they won 3 hits per hand. These were all statistically significant. We ran a lot of experiments. The standard error was only 0.4 to 0.6. So we can see pretty clearly that doing opponent modeling did much better than doing any of the exact Nash equilibrium strategies. Now, had we not, so some prior work on opponent modeling has done a really naive prior, where we assume that the opponent, not that they're playing close to Nash, but assume that they're doing essentially Dirichlet with parameters all equal to 2, so they're just doing random. And so if we take case samples sort of close to that random strategy and do the same experiments, we actually do really poorly. So you can't use a really stupid or really bad prior. It's important to have some sort of reasonable prior. Now the opponents, they're clearly not playing Nash, but that was good enough to use approximation of Nash equilibrium as the prior that we're sampling around. So it's important to use some sort of reasonable prior. If you use a really dumb prior, performance will be bad. Now I'm just going to briefly talk about, I have 4 different parameters. So here we have the epsilon. We chose it at 0.05. You can see even if you chose it at 0.02, 0.01, it still does pretty well. But if you go down to 0, it doesn't work. If you go up to 0.1 or 0.2, it does 0.4. So it's important, to have it somewhere in the region of 0.05, 0.03. For H, which was this burn-in period, it turns out actually we didn't want to have much of that in this game. We wanted to start exploiting right away. Other games, bigger games, this might change. You might want to have more of a exploration phase. So I think this is probably a parameter you'd want to tune in framing in general. This eta variance parameter, it turns out, didn't make too much of a difference. You can see the y-axis goes from like 45 up to 48, so it doesn't make too much of a difference. We chose 4, 2 is a little bit better. And finally, K, this is the number of samples, actually makes a huge difference. So we only did 10 because I wanted to run all these experiments, but had I used K equals 50, we would have had a win rate of 80 these experiments. And so having more samples makes it more likely that the opponents are playing something that's very close to one of the samples. Now, it's also going to make the agent run slower and take more memory. And so it depends on what your resources are. In general, you probably want to pick K as large as possible, given whatever your computational constraints are. And so just to wrap up here what I presented, so Nash equilibrium is pretty compelling. It's optimal, in one-card poker. It's a central solution concept in game theory. It always exists. However, I've argued that we really want to apply game theory to high-speed support in real-world situations, that it is not sufficient, it has significant limitations, and you shouldn't just follow Nash equilibrium. I think that's very problematic. So I went through 3 specific limitations of it. The first is that it assumes all players are perfectly rational, and Nash equilibrium is not robust to even a small degree of irrationality. I propose a new solution, safe equilibrium, that does address things. I also talked about a second limitation, that a lot of games, even simple 2-player zero-sum games, have multiple equilibria, even infinitely many. And so a real agent has to pick, which one should you play, and some might be better than others. I came up with this new concept of observable perfect equilibrium that I think is the right solution concept in sequential perfect information games. And the third issue is that it doesn't take into account if there's any data, historical or based on observations. It's not taking that into account. It's just basically following this table over and over again. And so I showed that if we do opponent modeling, we can get a much higher payoff than just by Nash equilibrium. I didn't go too much over the proofs of the theory and the details. If you want more information, these are based on some of my papers. They're all up on my website, ganzfriedresearch.com. And the final work, the opponent modeling, that was joint work with Kevin Wang and with Matt Chiswick. And so, yeah, that's pretty much it. And if you're happy to answer a couple questions, if anyone has some questions.
So let's assume we have like a 2-player heads up game. So assume player 1 is rational and player 2 has some incident that work. I guess my question is pretty basic. So is it guaranteed that, so you also talked about that infinitely Nash equilibria, and some of them being definitely better than the Nash equilibria in some way. So is it guaranteed that every single member of the set is going to be a winning competition?
Okay, good question. So actually, the safe equilibrium stuff I talked about is not for 2-player zero-sum games, because Maximin and Nash are the same in 2-player. That was for non-zero-sum games. So yes, it's true. Every Nash equilibrium is going to be unreasonable in expectation in a 2-player zero-sum game. Assuming you rotate the roles, like we saw in this game, the first player to act has a slight disadvantage, but if you switch roles, yes. So in a 2-player zero-sum game, every Nash equilibrium is unbeatable in expectation. Even, there might be infinitely many. They're all unbeatable in expectation, but some of them might do better against certain types of mistakes that the opponents are making, and so might be preferable in that way. So did that answer your question? Yeah.
So my question is, so I understand how the opponent modeling works, but can you elaborate more about how you exploit the opponent model once you get an understanding of its distribution?
Sure, so I can talk about, so the basic approach, and you can do other things. I wanted to just sort of talk about the basic thing, but the basic thing, once you build you know, you have the prior, you have the posterior, collect the observations, then it's actually pretty straightforward. You just play a best response. So you assume that they're playing, you know, you go through the posterior and you come up with the average strategy that you think they're playing. And then it's actually straightforward. I didn't go through how you can do the best response, but there's a efficient algorithm for doing that. And so that part is actually pretty straightforward. Now you might want to do something more. There's something called a robust response where you're not totally sure they're doing that. So you might want to do something a little more robust. But the basic idea here is that once you compute the model, you just play a best response to that. So like in rock, paper, scissors, if I think they're doing rock a little bit too much, the best response would just be, I'm going to do paper 100% of the time. So, but that's the idea. Does that answer your question? I didn't talk too much about the actual algorithm for doing the best response, but it's pretty straightforward. So, yeah.
I'm going to give an example of irrationality that will throw the national equilibrium.
Irrationality that can
Like will throw example of the irrationality, like you said, because the national equilibrium is not robust to.
Well, okay. I mean, the example I talked about very early on, I think highlights this, right? Like, what if player B there's some chance that they're crazy and that they're going to choose, that the column player is going to choose B, then we're going to get negative $1 million. And so, you know, the Nash equilibrium says, look, everyone's rational. Player 2 is not going to choose A, and it's 1.99 B. So a rational column player would choose A, and so we can choose B. But if there's some possibility that they're irrational, we would get negative $1 million. So this sort of highlights that.